In Chapter 2 of your text, we start discussing exactly how data is represented inside of a computer. Most of the stuff inside the chapter is pretty straightforward and isn't too hard to understand, but I thought I might go ahead and visit binary to decimal conversion or decimal to binary conversion using a little different method than what's in your book. The idea here is to give you an alternative to use. Some people really like the method in the book, and some people really like this alternative method. So it doesn't really matter which one you use, because the bottom line is you're still going to end up with the same result. Use the one that's most comfortable to you. Okay, so let's first of all start a little bit or discuss the notion of the limits of binary. There is a limit to the number of bits in a memory cell. Okay, back in the earlier days, probably the most productive computers that they had out there that finally made it to the desktop had memory cells that only had 8 binary digits, which was a byte. And the reason that we ended up with a byte was because a byte was a convenient size for encoding any letter in the alphabet, in particular using ASCII. Okay. Well, we decided we would go ahead and do that with numbers as well. We would just stay with a byte to represent the numbers. Now, they come in two glorious flavors. One of them is called unsigned, okay? That's what this should really say, is unsigned. Unsigned or sign magnitude. So if we have 8 bits, looking at all the combinations of binary digits from 0 to 1111, 1111, we can represent from 0 to a number as high as 255. Okay? But if we decide that we want to use both positive and negative numbers, we're going to have to basically divide that by 2, which means that we're going to end up with the lowest number that we can represent is negative 128, and the highest number that we can represent is positive 127. Now, those of you who are quick of mind are probably looking at those two numbers going, well, wait a minute, Dave, that is not a convenient division by 2. Something is up there. So, excuse me. So, yes, something is up, but we will discuss what that something is here in a minute or two, okay? With a 16-bit representation, we can represent, using unsigned numbers, anywhere from 0 to 65,535. But if we're going to use sign magnitude, then it's going to be a negative 32,768 to 32,767. Now I'll just go ahead and get rid of that space. Don't need that in there. Another thing that we have, another limitation with respect to computers, is in truth, computers can only add. They can't subtract, they can't divide, they can't multiply, they can't do any of that stuff. They can only add. So we have to come up with creative ways in which we can make a computer multiply or take a square root or anything along those lines. And what I'm going to do is I'm going to show you how subtraction occurs. From a mathematical perspective. This is exactly how a computer does it on the inside, so that you can get an idea that people do come up with clever little tricks to make a computer do what we really need to do. Okay? Another issue that we have is what happens if the result of our addition or subtraction is bigger than what memory can hold. Okay, that's a limitation. But for now, let's go ahead and let's look into the notion of subtraction. How do we subtract? Okay? Well, the very first picture that they had, or the very first idea that they had with respect to subtraction was, let's just go ahead and begin by converting the number into binary. All right, so we have a number that might be 7, for example, and then what we're going to do is we're going to complement the bits. And exactly what does it mean to complement bits? Well, it means that we're going to take all of the bits that are zeros and turn them into ones, and all the bits that are ones and turn them into zeros. For example, 7, there's a plus 7, is represented 0, 1, 1, 1 in binary. But negative 7, if we complement the bits, it becomes 1, 0, 0, 0, and it shows up as negative 7 in binary. Kind of makes sense? Well, one of the tricks or the challenges that we have here is now we have two numbers that represent 0. We have 0, 0, 0, 0 and 1, 1, 1, 1. Both represent 0. This is the positive 0, and this is the negative 0. And of course, those of you who are into using mathematics in the practical sense, positive zeros and negative zeros, pretty much don't make a great deal of sense, okay? But one thing is certain about this whole picture that we're looking at, and that is the most significant bit indicates that we are dealing with a negative number. No doubt some of you guys are asking, what? Most significant bit, what is that? Well, if I have 0000 and I change this bit in this position here from a 0 to a 1, it's only going to change it by 1. But if I change this bit from a 0 to a 1, it's going to turn it into -7. So it's going to make a huge change. Any changes of the digits on this side of the number make huge changes. Any changes of the digits on this side of the number, not such a big change, okay? So they say that this is the least significant bit because it makes the littlest change, and this one is the most significant bit because it makes the biggest change. So in ones complement arithmetic, what we do, the first thing we do is we convert the number to binary, okay? So we'll do that, 0, 1, 1, 1, and we turn that into a 7. The second thing that we do is we complement the bits. So we note the most significant bit after we complement it. There it is. There's 0, 0, 0, 1, because we're going to subtract 1 from 7. There's 1, so let's complement the bits. 0, 0, 0, 1 becomes 1, 1, 1, 0. And then we do something really, really clever, okay? We add them. We take the two numbers and we add them together, and we're depending on the limitations of the computer to turn this into the actually into the right answer, okay? So here we have our 0, 1, 1, 1, there's the 7, and now we're going to add 1, 1, 1, 0, okay? We're adding plus the -1. Down here we end up with a carry from here because 1 plus 0 is 1. 1 plus 1 is 0 with the carry, right? So now we've got a carry here, so 1 plus 1 is 0, and then we have another 1, so that becomes 1 with the carry. 1 plus 1 is 0 with the carry, and there's 1 that shows that our answer in fact is a 10101. The problem is the memory cell that's inside the computer can't hold more than 4 binary digits, so this critter has to be dealt with. And the way that we deal with this is we literally add it back into the numbers. So now we have 0, 1, 0, 1 plus 1 becomes 0, 1, 1, 0. So in other words, this bit that resulted in what's called an overflow gets added back into our number, and the answer is 6. And sure enough, if we subtract 1 from 7, we're going to get the answer 6. Pretty cool. Now it does have its pitfalls. Number one, it takes the electronics to pull this one off is a little more extensive than the electronics using other methods, okay? And the other pitfall is the fact that we have two sets of two binary codes, if you will, that represent a 0. So one of the solutions to all that was to use what's called 2's complement. So if I switch over to 2's complement, we're going to find that things are represented just a little differently, okay? The first thing we'll do is we'll convert the number to binary just as we did before. The second thing that we do is we complement the bits just like we did before, but now we're going to do something a little different. We're going to immediately add 1 to the result, okay? And just like before, the most significant bit is negative, okay? I'll just go ahead and say is negative indicator maybe or something. The most significant bit equals negative. How about that? 1 equals negative, right? So now the number is negative if the most significant bit is a 1, all right? So negative numbers always have a 1. Cool. I guess I should have read that a little bit better, huh? That's too funny. All right, let me leave well enough alone. Well, Control Z this, because there we go. That makes sense now since I read the whole thing. All right, so let's take a peek at this and see what we have. We had all zeros, right? To make a -1, complement them all. They all become 1 like so, right? So we end up with a 1, 1, 1, 1. Or no, I'm sorry, to make a -1, not a -0, because there is no -0. A -1. We say 1, 1, 1, 0, add 1 to it, and it becomes 1, 1, 1, 1. So you see what's happening here? So now we find, following the pattern, that the positive numbers work out as they did before, 0, 1 through 7. But the negative numbers, instead of this being a 0, this becomes a -1. And now I have one more digit that can be represented in this memory cell. That is, I can go all the way up to +7 or all the way down to -8. And that's why earlier when we were looking at the range of signed binary numbers, the negative side had one digit more in its range than the positive side. Okay, so let's do a little 2's complement arithmetic. Well, let's see. We first convert to binary, which we did. So there's 7's turned into a binary. There's our 1 that we're subtracting. Now we're going to turn it into a 2's complement. So we take the 0001, turn it into 1110, and then add 1 to it. Note that the most significant bit is a 1. This is a very good sign, because if the most significant bit becomes a 0, this will not work. Okay, it means that we have tried to create a negative number that is out of the range of our memory cell. Okay, so we then do our little handy dandy arithmetic. Okay, and this should actually say plus, not minus. So we add those two together and we end up with this result, right? 1 plus 1 is a 0 with a carry. 1 plus 1 plus 1 is a 1 with a carry. 1 plus 1 plus 1 is 1 with a carry. 1 plus 0 plus 1 is 0 with a carry. And now we have our carry just like we did before, except for this time the overflow bit gets discarded. This is a cool thing, because now I don't have to create electronics to handle that overflow bit, all right, to deal with it. So I've eliminated a step, if you will. It just goes into the bit bucket, as they say. So if you wanted to do like maybe 13 minus 9, you could give it a try, right? So here we are. There's our answer. 10. What in the world is this all about? The overflow bit was thrown out. I forgot to fix this slide. Gee, aren't you guys having fun looking at the mistakes that I just made in this thing? There is no 0. So we can get rid of this like so, and it becomes 6 there. Slide is fixed. Sorry about the mistake in the slide, you guys. I'm not going to re-record this thing because I'm well down the road to getting this done, and it's working out okay so far. Alright, so 2's complement is better. We get one more digit by giving up the -0, and the electronic circuits in an adder and subtractor are easier to build. Okay? So, what about floating point numbers? Well, let me discuss floating point numbers in the next part of the slide series. Okay?